Warmly welcome all of you to this year's Linné Celsius lecture. This is a tradition that's been going on for some 20 years or so at Uppsala, where we, in memory of two of our greatest scientists at Uppsala University, Carl von Linné and Anders Celsius, we are arranging lectures where we are inviting the most distinguished scientists from the world to talk about, to address topics of great interest for us here at Uppsala. This year we have Geoffrey Marcy from University of California, Berkeley, and Robert Hazen from Carnegie Institution in Washington, D.C. And they will give presentations. There is some, in a way, common theme, although they are in different scientific disciplines. My role here as Vice Rector, my name is Joseph Nordgren. I'm Vice Rector and responsible for science and technology area, disciplinary area at the university. My role is just to welcome you and hope that you will get an interesting and enjoyable afternoon. And there will be some more detailed presentations of the speakers by their dedicated hosts, professors at our university. So I will again welcome you, and I want to introduce the first host, Professor Nick Piskunov. Please.
Was it? Yes. Welcome everybody to the Celsius lecture, which will be given this year by Geoff Marcy. It was also interesting that Joseph Nordgren introduced himself. So for some people that never met, this was your chance. Usually in this kind of presentation, the host will go over dates and PhD defense and awards and various discoveries, but you can actually get some of this and most of this information from this little brochure that you got. Instead, I was thinking I will share my external observer impression of Geoff, whom I've known for 20 years plus. There are three features to Geoff as a person that always strike me as pretty unique. As a scientist, as a leading scientist, he managed to preserve some really beautiful human features that really attract young generation to his group and to his work, besides the fact that what he's dealing with is extremely exciting all by itself. And I'll just name those three things before giving word to Geoff. So first of all, he never gives up. He just keeps on going no matter what. And that is amazingly motivating for younger generation that sometimes can feel themselves left over or in a situation where desperation is just about to strike. So, just look at Geoff, and you just keep on going as he does. The second thing is often poor performance of your laboratory equipment can be a good excuse for not achieving your goals. That's not the case of Geoff. No matter how the equipment is performing, he will find a way to make the best out of it, or to find some alternative use. So keep your mind open and think, what can you do with what you have? And examples of that, I'm sure we will hear some examples of that in the presentation. And finally, I love the way Geoff interacts with younger generation of students. there is always discussion. There is never giving directions directly. It's all part of scientific discussion, and I think that's something we should, at least some of us, should really learn and try to implement at this university. With these words, I'll pass the place and the possibility to present his talk to Jeff. Thank you.
Well, thanks, Nikolai and Joseph, for those nice introductions. And I'd like to start by mentioning how happy I am to be here. I've never been to Uppsala University before, and I've wanted to come here for a long time. And I have friends here, and now even more friends. So I'm very happy to be here. And I'd also like to thank the organizing committee of the Celsius and Linnaeus lectures, because this is a marvelous tradition that obviously honors two of the best scientists and professors here at Uppsala. Today, I'd like to tell you some results that I think will be quite new. In fact, some of the results I will show you have never been shown to the public before. Many of them only being announced in the last few weeks, others never shown publicly at all. And it has to do with the search that continues for Earth-like planets, planets that have properties like our own Earth, in particular habitability, and ultimately the search for life and indeed intelligent life in the universe, something that the ancient Greeks pondered, and something that a 6-year-old child still ponders today. So I will tell you some results that represent the evolution of the astronomical and biological communities toward answering some of those questions. And I'd like to start by going way back 2,000 years, actually 2,400 years. Aristotle asked whether the Earth was unique, whether there were other Earths. And Aristotle had a clear answer that the Earth was at the center of the universe and that there were no other Earths because the Earth was clearly special. His disciples among Greek philosophers, notably Epicurus and Democritus that you see here, disagreed. And Democritus in particular, I have a quote here from him. He says, "There are innumerable worlds of different sizes. These worlds are at irregular distances, more in one direction, less in another. Some are flourishing, others declining." I think he's thinking about the Greek society there. Here they come into being, there they die, there they are destroyed by collision with one another. Some of the worlds have no animal or vegetable life, nor any water. Now you have to realize how remarkable this statement by Democritus really is. At that time, sitting around a table with his fellow Greek philosophers on a hot summer day sipping ouzo, they imagined that there were other worlds. Well, at that time, even the planets in our own solar system were not understood to be worlds like the Earth. Jupiter, Saturn, Mars were just simply points of light that seemed to move on the glass celestial sphere. Here, Democritus is talking about other worlds, indeed other worlds out beyond our solar system in his mind, since he's talking about thousands of them, and he's talking about biology on those worlds. So literally 2,000 years ahead of his time. And I think it's remarkable to recognize the foresightful imagination that really is the engine of human ingenuity in general, and Democritus certainly had it. However, the questions posed here about worlds and life outside our Earth remain mostly unanswered. We still don't know if there are Earth-like planets around other stars, and we still don't know whether there's any biology outside our own Earth. Here in 2011, The only life we've ever discovered is life here on the Earth, none outside. So the questions certainly remain. And of course, the most poignant and profound question is whether there might be intelligent life elsewhere in the universe, and we still to this day don't know the answer to that. So I'd like to begin with a more modern representation of recent history, and in particular our theories for the formation of other stars and planets. And the best way to tell this astrophysical history is to start with the beloved Orion Nebula. And I am going to try to turn down the lights, but I don't know if I can do it. So let me try, because I know this picture will look better with the lights down. Let's see if I can do that. I might turn down the lights in the whole building if I don't watch out here. Does anyone know how to turn down? I might need a little bit of help, because I think the picture will look so much better if these lights are off. It's probably one of this thing. Uh-oh, that's wrong. Keep trying. Ah, that's better. Isn't that better? That's good, actually. The backlights. Yeah. Uh-oh, yeah, you don't want that. That's good. That's very good, thank you. So the astrophysical history begins with the formation of stars and planets. And no better place to learn that history than the beloved Orion Nebula. If you look in the constellation of Orion, you all know the belt of Orion. Here's the sword hanging down from his belt. And the middle star of this sword is no star at all. It's actually the Orion Nebula, a large cloud of hydrogen and helium gases and other heavier atoms, within which stars are forming right this minute. And you can see some of the young stars that are condensing out by gravity, pulling the atoms together. Indeed, some very massive stars in the center, and then many other thousands of solar mass stars forming as we speak, these stars being only 1 million years old, a blink of an eye on the cosmic timescale. Those young stars have a story to tell. Because if you look at them carefully, here in the infrared light that pierces through the cloud, you can see how many stars there are that are being born out of the gas and dust. That's the Orion Nebula. And in fact, if you zoom in then with the Hubble Space Telescope, you see that those young stars actually have opaque slabs of gas and dust piercing through the star. Here's an opaque blob surrounding the star, seen in silhouette in front of the background nebulosity. There's a star covered by this black opaque blob, and you see more of them. Those black opaque stripes and blobs are in fact clouds of gas and dust, out of which the star is forming, but also out of which planets are forming around the star. So these protoplanetary disks, as they're called, are flattened, pizza-shaped configurations of gas and dust, so dense with gas and dust that the dust particles collide and stick and grow into full-fledged planets. And so this process and the measurements that come from these kinds of observations allow theoretical calculations of the formation of planets, and the theory is now fairly well established. You have a young star, and then around that young star is a protoplanetary disk of gas and dust orbiting the young star. The dust particles collide and then grow like dust particles will do when they collide into millimeter-sized particles and then kilometer-sized and eventually asteroid and full planets. And that's occurring here. beyond the snow line where it's very cold because of the distance from the star, there are not only dust particles, but ice particles as well, and they collide and stick into larger and larger objects, so you get comets and icy moons that we indeed see in the outer solar system around our sun. And then here you see a cartoon of the young star with many small particles that collide and grow into ever larger particles, eventually becoming planets. So the physics of planet formation in this theoretical framework is actually quite well understood. There are, in fact, a few remaining questions, not unlike the theory of evolution, but those questions at this stage are going to be overcome, I'm sure, in the next few years, allowing us to fully understand the formation of planets. So this is now a good theory, and of course the prediction is other stars should have planets, so let's go and try to find them. And it turns out, to cut right through to the modern era of this year, that there's a new method for detecting planets which is frankly superior to past methods. I'll talk about two methods, but the one that is looming as clearly more efficient is a method of detecting planets that is extremely simple. You simply watch the star and see if the star dims as a planet crosses in front of the star, blocking a small fraction of the starlight, telling you immediately that the planet exists and what the size of the planet is from how much light it blocks. And I have a few slides to show how this works. The technique is very simple. A child can understand it. As a planet crosses in front of the star, you simply measure the brightness of the star. You cannot see the planet. It's not resolvable with modern telescopes, even the Hubble. But you can measure the brightness of the star. And the more precisely you can measure that brightness, the smaller the planet you can detect when it crosses in front of the star. So this is a marvelous technique, and it's best done, frankly, in space. Above the Earth's atmosphere, you can measure the brightnesses of stars to 1 part in 10,000, and even better. And so luckily, NASA understood this a few years ago, began building a telescope called Kepler. And I'm lucky, frankly, to be a member of the team, the Kepler team. I'm one of the co-investigators. We've had a lucky and marvelous ride so far, and I'll tell you a lot about the Kepler results that are all new. But I wanted to show you the launch that took place at the Kennedy Space Center. Actually, this slide is out of date. It's now almost 2 years ago, as you can see, that the launch happened. It was a very emotional time for my wife Susan and me. We were there, and the whole Kepler team was there, and we stood on the beach, and we were so frightened that the rocket would go up and then go into the Atlantic Ocean. But that didn't happen. Kepler went up successfully, and now I'll tell you a little bit about the mission. It's a 1-meter telescope, 1 meter in diameter mirror, and it's monitoring over 100,000 stars simply with one purpose: to measure the dimming of a star as a planet the size of the Earth crosses in front of that star. Here's what the telescope looks like optically. Again, a 1 meter diameter. There's a mirror down at the bottom, 1 meter in diameter. It's got a very wide angle field of view, so it takes a picture of actually about 150,000 stars every snapshot. Every 6 seconds, it takes another picture, and it stores that picture. And then it adds that to the other pictures. And after 30 minutes of adding up all of these 6-second exposures, you end up with one final image that represents the sum of the light during those 30 minutes. That's all that Kepler does. It's a big camera that takes a picture integrated every 30 minutes. So the pictures happen 6 seconds. We can also add them up every minute, but most commonly, we wait for 30 minutes. We're going to do this for 3.5 years, if we're lucky 4 years, and we'll ask for an extension. And the precision is really what's dramatic here, that we can measure the brightnesses of stars to plus or minus 0.002%. That's about a factor of 100 better precision than you can achieve with a telescope located on the surface of the Earth. So this is quite a special attribute of the Kepler telescope, being above the atmosphere and then having a very stable, temperature stable and mechanically stable camera. You can see here that the other key is that it has a very large detector, 95 megapixels of CCD real estate at the back to take these pictures, which allows us to capture an enormous field of view, 10 degrees by 10 degrees on the sky. And we simply take picture after picture of the same exact part of the sky in the constellation Cygnus. Right here, you can see it's very near the galactic plane, the Milky Way plane. There are many, many stars, a high density of stars that gives us 100,000 of them every snapshot. And that's why we chose the galactic plane. And the telescope never moves. It simply stares at Cygnus and has been doing that now for 2 years. And we don't plan to move it at all. Now, let me cut to some of the exciting results. And one of the exciting results was just announced on January 10th of this last month. So now it's only 5 weeks ago, 6 weeks ago. And that was a star we call Kepler-10. And I'm going to walk you through the data that we took, and there's quite a few steps along the way, and I think you might appreciate seeing the actual data and then seeing the analysis that we do with Kepler to establish this planet around Kepler-10. And so here's the idea. There's the Kepler Telescope. It was staring at this star, and I'm going to show you where that star is in the constellation Cygnus. You can see Cygnus, the swan. It's obviously a swan. And there's the 42 CCDs that Kepler uses to take picture after picture. And then you zoom in on one of those CCDs, you can see how many stars the Kepler telescope is monitoring, this 150,000 stars. And as you zoom in, you'll see Kepler-10 appear. That's the actual image from the Kepler telescope. And now we'll go to an animation showing you what it looks like. So there's the star, and then the planet blocks a very tiny fraction of the light from the star, as you'll see in the data. So here are the data. These are the actual data from the Kepler telescope. You're seeing the brightness of the star over the course of some 200 days. And every one of these dots represents another measurement during 30 minutes of the brightness of the star. And what's really important is to look at the scale on the vertical axis. You see the scale has been normalized to 1 at the average brightness of the star. But here, this tick mark is 0.9995 of the brightness. So this distance from here to here is only 5 parts in 10,000. And you can see that the noise, the scatter, is only 1 part in 10,000, actually a little less than that. Unprecedented. Never before in the history of astronomy have we been able to measure the brightnesses of stars repeatedly to this level of precision. Now, if you look carefully at these data, you can see a planet with your own eyes. You'll see that the data go along, and then there's a dimming, and then the star goes back to its normal brightness, and then there's a dimming, and then back to its normal brightness. The dimming is only 5 parts in 10,000. Here's another dimming and another one, and I've outlined them here with these dashed lines. That repeated dimming of the star by 5 parts in 10,000 over and over and over and over again, that repeatedness tells you without question that there's a planet orbiting the star. Every single orbit it crosses in front, blocking 5 parts in 10,000. Immediately you know that pi r squared of the planet is 5/10,000ths of pi r squared for the star, the area of the planet being very small compared to that of the star. But that planet is not the one of interest. If you zoom in on this little patch of the data, notice that one of the transits, as we call them, is located right in that patch. If you zoom in, you see this. There's the planet that you saw by eye, but now if you look carefully, you'll see there's a dimming here, and another one here, and another one here, 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 and so on. Those dimmings are also repeated over and over and over again, but the time between the transits is a little less than 1 day. A planet apparently orbiting the star, taking less than 1 day to orbit, 0.84 days to be precise, and it's clearly an even smaller planet because the amount of dimming is now only a little less than 2 parts in 10,000, an extremely small planet. And in fact, if you zoom in on the individual dimmings, in fact, take all of the dimmings and fold them on top of each other, you get this plot of the dimming of the star right there. And you can see that it's only a little more than 1 part in 10,000. A planet clearly with a radius such that its area is a 10,000th that of the star. And you can measure the so-called transit depth here, and it's 0.00015, telling you how large the planet is, essentially unambiguously. And it turns out, since we know the radius of the star, because we know its spectral classification, indeed it turns out to be a sun-like star within 5 or 10%, it's almost the same as the sun, that the planet has a radius of only 40% more than that of the Earth. So this is a planet 40% bigger than our own Earth. And I think what's remarkable is how obvious the signal is. You know, you can see this planet a little bigger than the Earth with your own eye. No Fourier analysis or complex multivariate least squares fit. You can just see it's a small planet right there. And the period is very short, a little frightening. This is apparently a planet a little bigger than the Earth that takes a little less than 1 day whipping around the star. Here's another cartoon that summarizes all of this. There's the cartoon of the planet crossing the star, the dimming of the starlight that Kepler measures, and then here are the actual data giving you this radius of 1.4 times the radius of the Earth. So this is what we think it would look like. This, of course, an artist rendering. And I remind you, we don't have a picture of the planet. We don't even have a photon, not a single photon from the planet. And yet we know its orbital period, and hence how far the planet is from the star. And we know the size of the planet without any question. Now, there's one remaining issue, and that is, first, are we fooling ourselves? Did we make a mistake? Are we misinterpreting the repeated dimming? Could it be a background eclipsing binary star that somehow is fainter than the main star, Kepler-10, and is giving us the impression of a transiting planet, but actually it's a background double star that eclipses itself? And secondly, what is the mass of this planet? If it is a planet, can we determine its mass? And you can see why we want not just the radius, but the mass. Because if you have the mass and the radius, then you have the density of the planet, critical for determining the composition of the planet. So I'd like to now spend a couple of minutes and describe the measurement of the planet's mass by using a different technique. And that technique involves measuring the Doppler shift of the light from the star. And here you see a graph of the measured velocity of the star for Kepler-10 over the course of one orbital period, and the data points show the Doppler measurements. And you can see that indeed, during 0.83 days, the star's velocity, as it was measured, went up and then down and then up again. Why would the star do that? Well, the star, of course, would do that because it is being gravitationally pulled by the planet. And so we're measuring the gravitational mass of the planet by measuring the Doppler shift very precisely. And so the basic idea is this: if you have a star with a planet, the star, of course, will not be stationary. It serves as a sort of a target, like in high-energy physics, and you can see the recoil of the star due to the planet. We measure the planet's mass from the motion of the star. And we do that with very precise Doppler measurements. Of course, our sun, our own sun, executes a wobble in space due to the 8 major planets: Mercury, Venus, Earth, Mars, and Jupiter being the big bully, Saturn the second largest bully, yanking on our sun. Here's where it was in 1960, 65, 1970, 75. So our sun moves around, betraying the existence of the 8 major planets, and also revealing the masses of the planets in our own solar system. So we do that technique for other stars. And the idea is to simply measure the Doppler shift of the light from those stars, thereby allowing us to detect a periodicity in that Doppler shift, telling us that there's definitely a planet, what the period of the planet is, and most importantly, what the mass of the planet is from how strongly it grabs the star. Now, the hard part actually is measuring this Doppler effect. It's very small. It's literally a few meters per second is the speed of the star, which means that V over C, the velocity of the star divided by the speed of light, is typically about 10 to the minus 8. So we have to measure wavelength shifts to 8 significant digits to detect this. We use the Kepler Telescop on the Big Island of Hawaii, and it has a marvelous spectrometer that spreads the white light from the star into all of its composite colors or wavelengths of light. And then we record that spectrum with a digital camera, and it looks like this. The hard part is detecting the tiny Doppler shift. So what we do is we zoom in on the dark spectral lines on the computer, and we watch to see if those dark spectral lines move back and forth, allowing us, and this is magic, to detect shifts of a fraction of 1 pixel on the CCD. Indeed, we can measure Doppler shifts to plus or minus 1/1000th of 1 pixel on the CCD. And you can see how that works. We can measure the amount of light in the neighboring pixels, and the amount of light goes up and down as the dark spectral line moves back and forth. So by measuring very precisely the amount of light in the neighboring pixels, we can determine the position, the wavelength of that spectral line to within 1,000th, even frankly a 10,000th of 1 pixel, assuming we have very good photometric precision in our spectra. So this is the kind of activity that we're engaged in. And by the way, Nikolai is one of the greatest practitioners of this, helping to establish new techniques for measuring this tiny Doppler shift. Okay, so that's what we do. Here are the data. This now is Kepler-10, the actual data for Kepler-10. You're seeing the velocity of the star over the course of 1 orbital cycle. And I want to call your attention to the vertical axis again. In this case, we're measuring the Doppler effect, and you see that the scale only goes up to 5 meters per second. Well, 5 meters per second is about this fast. Human jogging speed is 5 meters per second. The Olympic runners, of course, run the 100-meter dash in 10 seconds. So we are actually measuring the speed of a star that is, by the way, about 1,000 light years away. And yet we're determining the speed of the star to within plus or minus human jogging, human running speed. And in fact, the amplitude of the velocity variation is only about 3 meters per second, almost a fast walk. So it's amazing that the technology that we've been developing allows us to do this. And it tells us, therefore, that the planet really does exist. It's not a background eclipsing binary star. And moreover, it tells us the mass. The larger the mass of the planet, the higher the velocity amplitude of this Doppler shift. And you can see that we deduce a mass of 4.6 Earth masses. 4.6 Earth masses. And that, of course, should be compared immediately with the radius, which I already told you is 1.4 Earth radii. So now we have a mass and a radius, and that allows us to determine the density. And it turns out we get 8.8 grams per cubic centimeter. Here's sort of the summary. From the transiting planet and the brightness change, we get the size in radius of the planet, and from the Doppler measurements, we get the mass. And mass divided by volume tells us the density. Now, 8.8 grams per cubic centimeter is a marvelous number, I think. And the reason is that I don't know too much chemistry, and I don't know too much mineralogy, but I do know that the density of water is 1 gram per cubic centimeter, and I know that the density of the Earth is 5.5 grams per cubic centimeter, the global density of the Earth. This planet has a density higher than that of water and even higher than the density of the Earth. So it's assuredly a solid planet. It cannot be made of gas, and it cannot be made of water or some other liquid. It has to be solid, and indeed even more dense than the Earth. And there's two reasons it might be more dense than the Earth that are quite obvious. One is maybe this planet, because it's larger than the Earth, suffers more gravitational compression, the mass of this planet pressing down on itself, compressing it to a somewhat higher density. And also, the other possibility is that the planet has a higher proportion of iron and nickel compared to silicates than does the Earth. And both of those possibilities are quite plausible. And so I show here a plot, it's a bit of a sophisticated plot, of the mass of hypothetical planets in Earth masses and the radii of those planets in Earth radii. Here's 1.0 and 1.0 mass and radius, and indeed I've plotted the Earth. There's Venus, there's Mars, and you see Kepler-10 is right here. Kepler-10 has a mass of a little more than 4 Earth masses and a radius of 1.4 Earth radii. And I've drawn some curves, solid curves. Here's the curve where the planets would reside for an Earth-like interior composition, silicates and an iron and nickel core. The planets of that composition lie along this line. If the planet instead is pure iron, it would lie along this line in the mass-radius domain. If it's pure water, it lies along this line. Higher radius, of course, for a given mass, lower density. But Kepler-10 sits here. And you can see right away that it has a density that's intermediate between that of an Earth-like composition and an iron composition. So either that's because of the compression, or it's because the planet has more iron, and maybe both, for all we can tell. And there's an uncertainty in the mass from the Doppler measurements, and that leaves us a little uncertain as to what the actual mass might be. So we can't tell exactly where Kepler-10 resides. But these are 1 sigma error bars, so they're quite good. Now, of course, without a picture of the planet, and indeed without even 1 photon from the planet, we call upon our next ally, the artist. And here you see an artist's rendering of Kepler-10 with a little hint of iron and nickel thrown in. And I think I now have a movie to show you what the planet might look like if you could take a spacecraft with a camera and fly close to Kepler-10. There's the planet seen in silhouette by which it was detected. It's certainly solid, so we've depicted it as a solid rock, maybe with more iron. It's so close to the star that the inner edge of the planet is blowtorched. The planet is certainly solid, but blowtorched by the enormous radiation from the star. And the surface of the planet would be very hot, something like 2,500 Celsius. Maybe even some of the metals on the surface being molten. And so here's the artist's depiction, a little fanciful and certainly imaginary and probably wrong about what the planet looks like. We don't think it would have an atmosphere, and we don't think it would have any water because it's just simply too hot. The molecules would achieve escape velocity and leave the planet. Still, you can see that we would love to have the day arise when we could actually take pictures and even take spectra of planets that are rocky like this one is. Now, I'd like to move my attention to what we announced a couple of weeks ago. Literally on February 2nd, we made a new announcement, and these are very fresh, so I'd like to walk you through them. We announced from Kepler 1,200 new planets. We call them planet candidates because we haven't verified the existence of any one of them with 100% certainty, but I can tell you that they are 90 to 95% actual planets. A few percent of them are not planets. We've been fooled in some way, like a background eclipsing binary. But 1,200 new planet candidates, some of us call them plandidates, is quite exciting. Most of them, the majority, are nearly the size of the Earth. This is startling, stunning, and revolutionary. These are 1,200 planets, most of which are literally a couple times, 3 times the radius of our own Earth. So quite an amazing new turn of events for planetary science. And one of the stars has 6 planets orbiting it. I will show you some that have 2 planets, some with 3, all of which transit, 4, 5, and this one, 6. So I'll tell you a little bit about these. I'll remind you we've been monitoring 100,000 stars. Thanks, Nikolai. And here's where they reside in the Kepler field of view. You see the stars are scattered all over, the planets and their host stars are scattered all over the map. The planets have different sizes. Some of them are Earth-sized. Some of them are a little bigger than Earth. We call them super-Earths. Some of them are Neptune-sized. I've color-coded them here. So we're seeing planets of all sorts of different sizes. And here's a very interesting plot, actually, of the equilibrium temperature of the planets. How do we know the temperature of the planets? Well, we know the temperatures because the distance of the planet from the star we know from the orbital period, and the farther the planet is from the star, the cooler the planet is. And sadly, with this being the Celsius lecture, this slide was made by NASA. And therefore, it has units of Fahrenheit. I'm very embarrassed to admit, but it's my country and there's not a darn thing I can do about it. But you get the idea. There is a wide variety of temperatures for the planets. They scatter in sizes and also in temperatures, and most interestingly are the coolest of the planets. These are the planets in this domain that have a temperature roughly that of our own Earth, something like between 0 and 100 Celsius. And we can zoom in on those planets with Earth-like temperatures from here down to here, and you can see that we've found something like 50 planets with Kepler that have temperatures such that any water on those planets would be in liquid form, not in steam, not in ice, but liquid. And of course, liquid water is the prerequisite for biology, at least as we know it. Moreover, we can plot the number of planets as a function of their size. And you see here, never before shown, by the way, the number of planets and their distribution as a function of the radii of the planets. Here's 4 Earth radii, 2 Earth radii. And you can see that the number of planets simply increases like a power law very rapidly with smaller and smaller sizes. There are hundreds of planets now found with Kepler that have sizes of only twice that of the Earth, even a few percent larger than the Earth. And so it's an amazingly new era that just dawned 2 weeks ago, in which we can study now planets that are just slightly larger than our own Earth in large numbers. Now, I mentioned that the most interesting multi-planet system is one with 6 planets. And here it is. Well, it's an artist's rendering of it. You can see the star, 6 planets. I will show you what the system looks like. All 6 transit. They all show a repeated dimming of the star with 6 different periods, very clearly mapped out. I think we have 85 transits now. So it's very clear that all 6 planets exist. We know their radii, we know their orbital periods, and here's a sketch of that system compared to our own solar system. All 6 planets orbiting closer in than does Venus from our sun. So this is an amazing multi-planet system, and here's NASA's movie for this 6-planet system. Quite accurate, I might add. They all transit. What's profound is the architecture. These planets lie in a very thin, flat plane. And of course, that's beautiful, because the theory of planet formation that I mentioned at the very beginning predicts that planets should form in a very thin, flat plane with all the planets going around in the same direction as they do in our own solar system. And you're seeing here a clear representation of a planetary system that agrees perfectly with the theoretical expectations from those protoplanetary disks. And here's another plot of the masses and the radii of these 6 planets. Actually, only 5 of them do we have masses for them, B, C, D, E, and F. And you can see that these planets reside at higher radii than Kepler-10. And so these are less dense. We think they have a thick envelope of water, probably a gaseous atmosphere as well. So these are more like Neptunes or Uranuses, maybe even like Saturns, albeit quite small. So we're seeing planets that are like the Earth, but with more liquid and gaseous components to them. Moreover, Kepler has found 150 planets, 150 stars with multiple planets. And I'm showing you here a crazy movie that shows you literally all 150 of the multi-planet systems that Kepler has found. So it's an amazing menagerie, a zoo of systems that we can all now study. These are public. You can ask for telescope time, study these planets with any telescope you want, measure any property you want. So it's quite an amazing era. Now, I'd like to spend the last 6 or 7 minutes talking about something that I know nothing about. And so I could well be quite off base. And as you can imagine, I'd like to turn my attention with some embarrassment to the possibility of intelligent life on these Earth-like planets. What can we say in the modern era about intelligent life in the universe? Well, there's some quantitative information. We know that our Milky Way galaxy, from the surveys that I've shown you, our Milky Way galaxy with its 200 billion stars has at least 30 billion planetary systems. Many of them have Earth-like planets, as you now know, and so the only question that arises is a biological question. What fraction of those Earth-like planets spawn primitive life, and then what fraction of those lead to intelligent life? Well, we don't know the answer about what fraction of Earth-like planets lead to intelligent life. The most pessimistic answer I've ever heard is that intelligent life is 1 in a million throw of the biological dice. And if you adopt 1 in a million and multiply by 30 billion, you immediately see that our Milky Way galaxy, never mind the other galaxies, should contain thousands of civilizations, many of which have been around far longer than our own human civilization, meaning that those civilizations are more advanced. The prediction is clear. Our Milky Way galaxy should contain thousands of technologically superior beings. And of course, this is exactly what the science fiction writers have been telling us. They wrote novels for 100 years. They've worked on science fiction movies like Star Wars and Star Trek. And of course, the depiction is indeed a galaxy filled with intelligent life. But is that right? Is there a mistake in this notion? I'd like to propose that maybe the science fiction writers, and even my little calculation, could be wrong. And one of the reasons it might be wrong is simply the data. We don't see the advanced civilizations. With our telescopes, with all of our sensing techniques, the moon has footprints on it from explorers, but they're our footprints. In 4.5 billion years of the moon without any friction, no air, no wind, there's no evidence of other beings that left footprints literally or metaphorically on the moon. There's no obelisk, no camera left by an advanced civilization. Now we have high-resolution images of Mars, and there's no evidence that any advanced civilization in 4 billion years set up a laboratory on Mars, cameras, seismometers, X-ray devices. We've ventured to Mars, but this galaxy teeming with intelligent life has failed somehow to explore Mars. Why? The Earth is an amazing trap for advanced species. The Earth, of course, is very habitable. We have beachfront property. We have lush tropical rainforests. Why didn't these very intelligent advanced species come and explore, maybe colonize, as we humans have done, exploring the surface of our own Earth? Why didn't the other advanced species come and set up a settlement here on the Earth itself? It's very surprising that they didn't do that. So the lack of intelligent life on the Earth, present company accepted, is a sign that maybe the galaxy is not teeming with intelligent life. Moreover, professional telescopes, hundreds of them watching the night sky every night, have never seen a good clear picture of a UFO or advanced aliens approaching the Earth. We don't see the gamma rays that we would have seen if there were matter-antimatter engines out there, like the Starship Enterprise. We don't see robotic probes. Forget the difficulties of traveling to our solar system from afar. They could just send little tiny cameras with robotic probes, but we don't see them. Moreover, many astronomers have been using radio telescopes to hunt for the radio and television transmissions from these advanced civilizations, and after over 40 years, still the search for extraterrestrial intelligence has failed to find even a single signal. So we cannot ignore the many non-detections of advanced intelligent life. Yes, you could explain away one or two of these, but all of them added together gives you pause. Maybe our galaxy has fewer intelligent civilizations than we had thought. So the question is, where could we have gone wrong? Did we overestimate the population of advanced species? They could have wandered here blindly, but they haven't wandered here. So where are they and why aren't they here? Well, one possibility to speculate is that our own Earth is more special than we had thought. It turns out that our Earth is 0.03% water. If our Earth had 0.02 or 1% water, that water would be soaked into the mantle, and there'd be very little for oceans and lakes, if any, and the Earth would therefore not have acquired as much water from asteroids and comets, and it could be a desert planet, like Mars and like Venus. No water on the surface at all. Alternatively, the Earth might have acquired 0.06% water. Then, of course, there'd be so much water on the Earth that the continents would be covered, even covering perhaps Mount Everest. And so we would have a water world. And again, yes, primitive life, even marine life, would be easily possible. But technology, such as musical instruments, electronic circuits, rocket ships, pianos, would not be possible on a world that was simply covered by water. Now, another reason intelligent life might be rarer in the galaxy than we had thought is that maybe Darwinian evolution simply does not lead inexorably toward intelligence. Maybe big brains are more rare and the dexterity to build tools are more rare. And the best way to test this hypothesis that intelligence is perhaps not guaranteed is to look at the fossil record of other species on the Earth. The paleontological record is very clear that, in fact, species on the Earth tend not to get smarter over millions and millions of years. And there's no better example of this than the dinosaurs, who ruled the Earth for 100 million years. And their brains never got bigger than the size of chicken brains. Imagine a mother dinosaur. She just laid her egg. It's a little baby dinosaur, and she's hoping that her baby dinosaur will be a high IQ dinosaur, a smarter dinosaur, and of course that smarter dinosaur would be able to outcompete the other dinosaurs, and that dinosaur would pass on its intelligence genes to the next generation. Well, if that were true, then dinosaurs would have gotten slowly but surely more intelligent. But the paleontological record shows that the brains of dinosaurs, the encephalization, never really increased at all. So intelligence didn't help them survive, help them pass on their genes to the next generation. And that's true for most other species throughout their history. Indeed, even the pets that we enjoy, like cats and dogs, insects don't get smarter over the geological record. Studies have been done of insects. They're just not getting smarter. Cats and dogs are not getting any better at their music lessons. And it's remarkable, really. I mean, it's silly. But on the other hand, why don't dogs get smarter and smarter? And it's because intelligence doesn't drive evolution as much as the other attributes that these species enjoy. So Darwinian evolution might not point toward intelligence. And in fact, there are some species on the Earth that have survived for 100 million years and have no brains at all. And I think the most spectacular example are jellyfish. Jellyfish are, of course, boneless, but jellyfish are also brainless. And they've done very well, thank you very much. And so you get the idea that we humans perhaps have been arrogant in thinking that intelligence puts us at the pinnacle, the top of the evolutionary tree. But of course, the biologists know, both from a microbial standpoint, from a DNA standpoint, and from an evolutionary standpoint, that we humans are not at the top of the tree. So maybe we humans with our big brains are more of a fluke, a lucky throw of the dice that happened on the East African savanna than we normally like to think. And then the last thing I'll say is that, of course, even when big brainy species do arise in the Milky Way galaxy, perhaps they develop the means for their own destruction, either with weapons or with the demise of their environments, not taking care of their home planet. So it's possible that intelligence is sort of self-regulating, that when you become too smart, you become a threat to yourself, and that would limit the number of advanced civilizations that might be in the Milky Way galaxy at any given time. Our lifetime as an intelligent technological species just simply might be limited. And so I'll finish by saying that I think one of the great experiments that we humans should be engaged in is the search for intelligent life. We are doing very little. We spend very little money internationally on the search for extraterrestrial intelligent life. And I would like to propose that somehow internationally we gather our funds and build a large radio telescope array to be able to detect the advanced species that might be transmitting radio or television waves. And we can pick them up just by spurious radio transmissions that are floating throughout the Milky Way galaxy. And of course, we know where to point our radio telescopes now because we have these Earth-like planets from Kepler. So we should just be pointing at them, at least to start, to see if there's any intelligent signals coming from them. So I'll finish by saying that we are in a special moment. It's hard to recognize a historical moment in scientific history, but I think we are in a special moment. The first Earth-like planets are being detected. Earth-sized planets are almost certainly common, as you saw from the Kepler results. But intelligent life might not be guaranteed. It might not be very common. I think primitive life that requires only a cell wall and replicating DNA-like molecules, primitive life is probably very common. But it's the technological life that I think is still in question. And it could be that our species here on the Earth is one of the rare intelligent species within the Milky Way galaxy. So I'll stop there. Thanks.